So we might ask the question, now that we do have this technique, a chain rule, for our indefinite integrals, how does this apply to our definite integrals? And actually, there's a nice little trick that we can use here by substitution that actually shortens the amount of work that we have to do. I will explain. Let's say that we have this antiderivative right here. And of course, we know that as an antiderivative, if we said let's let u equal the quantity 1 plus 2x squared, as we should, because that's the quantity under our square root right here, we would find that the derivative of u is going to be 4 times x dx. We definitely have an x dx. We're going to have to handle this 4, so we're going to treat this as 1/4 of du when we replace x times dx. And so in our antiderivative, we might express this as an antiderivative of 1/4 of u to the negative 1/2 du. Now we might think to ourselves, okay, well, let's just go from x equals 0 to x equals 2. But notice that we've changed the variable. U is now what we're taking the antiderivative of. We're no longer in terms of x. How does that affect us? Well, the time-saving nice thing right here is that we can actually substitute in 0 for x right away. Right? If we let u equal 0, we're going to say, well, that's 1 plus 2 times 0 squared, which is just to say 1. And of course, if we let u equal 2, which is at the upper end, our upper limit of integration, we're going to have 1 plus 2 times 2 squared, which we know to come out to be 9. And so our integral right here will be the integral from u at 0 all the way up to u at 2, which is going to be from 1 to 9. And look at what effect this has. This tells me that I'm going to take 1/4 times, and when I use my integral right here, 2 u to the 1/2 evaluated from 1 to 9. I'm going to factor out my 2 in front right here. I'm going to have 1/2 of the square root of u from 1 to 9. And notice, right, we're dealing, u is 1 and u is 9, so we're going to get 1/2 the square root of 9 minus the square root of 1, which is to say 1/2 of the quantity 3 minus 1. 3 minus 1 is 2, and 1/2 of 2 is 1. Well, that's sort of interesting. Now, wait a minute. How did I know I could do this? Let me just back up one moment right here and show you what would happen if I hadn't made this replacement right here. So I'm going to take my step right here where I rewrite this and just show you this. So right here, instead of writing 1/4 from 1 to 9, which is what we get here for u, I rewrite it this way: 1/4 of the integral of u to the negative 1/2 du. But this time I don't change that variable. I say, well, this is from x equals 0 to x equals 2. What's going to happen? Well, for one thing, I am going to take my antiderivative as I had right here. So I would have 1/4 of the quantity 2 u to the 1/2. Only this time, I didn't change my variable. I said, well, this is x equals 0 to x equals 2, right? Is this the same value that I get over here? Well, I have to actually replace 2, so I'm going to take out my 1/2 as I did before, only this time I'm going to make it the square root of 1 plus 2x squared. And now I can get rid of the variables right here, and I'm going to treat that from 0 to 2. And do I come up with the same thing? Well, yeah, I do, because I'm going to have 1/2 times the quantity square root of 1 plus 2 times 2 squared minus the square root of 1 plus 2 times 0 squared. Correct those things in there. It looks kind of awful under that root. Let's try that again. 1 plus 2 times 0 squared. Well, of course, sure enough, that's 1/2 of the square root of 9 minus the square root of 1. And as shown before, yeah, we get 1. Definitely. So it's a matter of where you want to make the replacement, and sometimes just making the replacement right away in terms of x, even before we begin our problem, saves us a little bit of time when trying to find our value later.